back to the saturated liquid vapor mixture curve. And here's the curve. Okay. And, or I could say back to the bell curve. Right, and this could be pressure or temperature. And this side of the bell curve represents the saturated liquid line. And this side represents the saturated vapor line. And inside I have a liquid slash vapor mixture. And we introduce this new symbol or new subscripts VFG. So this is specific volume, and right here is V sub F and V sub G. And F represents the fluid, G represents gas, and FG represents liquid vapor mixture. So, specific volume of a fluid gas mixture. If I'm on the line, I have all fluid. If I'm on the line over here, I have all gas. I could be up here, again, all gas. So it's saturated. Superheated vapor in this region. Subcooled liquid or compressed liquid in this region. We introduced this idea of a quality factor and X, or quality. And so X typically is expressed in regards to the mass of vapor relative to the mass total. And so I could say mass vapor, mass total, or I could say mass of the gas with G, following the same subscripts as over here, mass total. Where the mass total is equal to the total amount of mass in the liquid state plus the total amount of mass in the vapor state, and using these other subscripts, MF plus MG. So pretty straightforward, right? So back to the bell curve, temperature, pressure doesn't matter. And so I want to discuss the ramifications of this VFG, because a lot of times in your calculations you'll be looking at the vapor quality or the quality factor. So X also can be called vapor quality. But nevertheless, it represents the percent, or the amount of mass of vapor in my control volume relative to the total mass. Mass fraction of vapor in a saturated liquid vapor mixture. So I talked about this idea of a control volume. So here I have a box where the red dots represent vapor. This is a control volume. So the magnitude of the volume of the control volume is dependent upon what you are interested in looking at. So if you're looking at microfluidics or some biological things, testing fluid flow or some thermodynamics of biological processes related to someone's blood, then you're going to want something much less than a control volume of a 1 centimeter cubed. However, if you're looking at gas turbines that are going to be used in at power plants, right? So whatever it might be, gas turbines for generating electric power, then 1 centimeter cubed is pretty small. So it's all dependent. Nevertheless, the idea of defining a control volume is essential. So I think there was like 10 or 15% of the class is actually taking fluid dynamics right now. So you're probably starting off in the class talking about defining a control volume. And in this class, we're talking a lot about fluids or gases entering a system, something happening thermodynamically to them. There's a change in energy, right? There's a transfer of energy. And then it does some work, and then that fluid might be in a vapor state or a liquid state after. So control volume, defining it, very important. And so I can just do some pictorial thing where this represents liquid. And of course, if I know the densities of both, I can convert, if this is a volume, I could say a control mass too. But if I know the density of the liquid phase, then I can calculate the total mass of the liquid. So mass total follows the same as what we had before, but I'll just leave it as mf plus mg. And again, this can be pressure or temperature. And there's some corresponding temperature or pressure at this location. And again, I have my saturated liquid and saturated vapor lines. So control volume, mass total, mass fluid, mass gas. So volume total is going to be a total volume of the fluid phase plus the total volume of the gaseous phase. And of course volume, right? I can express that in terms of the specific volume and mass, because specific volume is just the volume per unit mass. So I get mass total equal, thank you, mass total times the average specific volume and then I can rewrite this as mass of the fluid phase times the specific volume at the fluid phase plus the mass of the gaseous phase times the specific volume of the gaseous phase. And this average specific volume, I can express that in equation form. So I have average specific volume, so that, thank you. So within here, I could pick some region, right? And I'm going to have a specific volume associated with that. There's a control volume, average specific volume. It's going to be composed of two components, that of the fluid and the gas. And I can write this in terms of the quality factor, 1 minus x times the specific volume of the fluid phase plus x times the specific volume of the gaseous phase. So when x is equal to 1, in my control volume, what is the percentage of vapor? X equals 1, what's the percentage of vapor? 100. So x equals 1. The average specific volume is just that of the gas, right? And then I can get a mixture, so this is just a number between 0 and 1. Okay, if we're talking about a little bit more complicated things, this number can actually be negative. Then we're talking about a subcooled liquid. Nevertheless, we're not going to deal with x less than 1, but in many heat transfer, heat exchanger type problems, you want to know if x is less than 0, and you want to make sure x is less than 0.9. There's some problems with the efficiency of the heat exchanger when x becomes greater than 0.9. Anyways, so if you take a course in thermal fluid sciences and engineering, you'll probably learn more about that. But in the context of thermodynamics, we just want to define an average property, average specific volume, and we write that in terms of the quality factor. Okay. And I can rewrite this a little bit differently. And in this case, I'm going to say the specific volume of the fluid plus X times the specific volume of FG. Now, in the last lecture, you couldn't see it on the through the videos anyways, because there was some problem with it, but I put a G here, and it can't be G. So, nevertheless, I have a specific volume of the fluid. If X is equal to 1, I add to it VFG, and it brings me out here. So this plus this difference puts me here. If X is equal to 0.5, then I end up right here. So this represents something like X.35. So I have that plus 0.35 times this gives me a specific volume right here. Or I can use this top equation, right? So it's just a rule of mixtures averaging. Pretty straightforward. But the convenience of the reason why I want to stress this is because it's convenient, because here we're using a thermodynamic property, and we're writing an expression for the average thermodynamic property, specific volume, and this also applies to internal energy. Entropy and enthalpy. So it applies to big U or small u, big S or small s, and big H or small h. So I can use this same type of format, and let's choose this one here. I like this one better. I always like to choose the expression with the least number of variables. When you start working on more complicated problems, it ends up being useful because you have less reasons to put in, have a factor or two error because you have less variables. But nevertheless, so the average internal energy within my control volume of a liquid vapor mixture, right? This has an average internal energy. It has an average entropy per unit mass, so internal energy per unit mass, and it has an average enthalpy per unit mass. So I have my control volume, has an average internal energy per unit mass, and just using the same type of expression, so I have the internal energy of purely the fluid phase plus X times UFG. Same, likewise, entropy per unit mass of the pure fluid phase, right at the saturated point of the bell curve. So I could plot pressure and temperature versus S here. I would have also a bell type curve. I would also have a bell curve, and so when I got up to the critical point, I couldn't distinguish whether I had liquid, whether I was fluid or vapor, so you'd still have this, and so you can see here as I go up, VFG, SFG, UFG approach 0. Nevertheless, let's go to here, SF plus X, SFG, and H, HF plus X times HFG. Now I just want to point out that this works well. Okay, so if we have really large values of internal energy and things like this, you start breaking down, but that kind of makes sense, right? If we have really large energies, we're probably not close to we're not probably indicative of an ideal gas. But even if these are if they're large in magnitude, it still works. But, if it's not working, then you really don't have a well-defined bell curve. So enthalpy, the average enthalpy within my control volume, which is a liquid vapor mixture, But if I'm 90% vapor, then I look up this value here, right? And I take out of the fluid times whatever this times 0.9 plus times 0.9 times this. This value here, what related to phase change, what is it? Does anybody know? HFG? Anybody know what HFG is? It's so in this bell curve, I could plot temperature, right, versus H. And when I'm on the saturated vapor line, I would have an HF. And when I'm on the saturated liquid line, I would have HF. So why don't I just do that right here? And I'll just plot temperature versus H. And right here I'd have some HF, HG, HF. Now, of course, given that I have a curve like this, and this represents a phase transformation, what is the pressure going from this point to that point? Constant. It's constant. So I have my pressure isobars, right? So here I'm 100% fluid, and here I'm 100% vapor. H has units of what? H has units of what? Just guess. Someone guess. Kilojoules per mole? Okay. You could say that. We're putting H in per mass basis, right? So there is a per number of moles way of writing these small U's, but in the back of the book and in the appendix, you'll see H listed as kilojoules per kilogram. So big H is energy, joules. So this represents amount of energy per unit mass to go from pure fluid to pure vapor at a given temperature and pressure, right? Because this is T1, and we know when we go through a phase change, the pressure is constant, so the pressure doesn't change, the temperature doesn't change. This is the latent heat of vaporization. Okay. So, freshman physics, we learn about latent heat. We say latent heat of vaporization, so it's L sub V, right? Now I could make these graphs more complicated, right? And I could put these other lines for when it goes from solid and when it goes from liquid to solid and all this other stuff. And so I'd have portions down here, which would mean from fluid to solid, and then I would have some other value right in here, and then that width at constant temperature and pressure would represent the latent heat of fusion. I just want to point out that as I increase my temperature, right, this value gets smaller and smaller and smaller. So remember when I talked about when the technician might come and look at your air conditioner and you're saying it's not cooling the house, and the first thing he does is check the pressure? So if the pressure is off, you might not be operating in here, or you might be in some regime where you don't have a large latent heat of vaporization. But typically, if the pressure's off, you're not going within this region here. The pressure is too small. You're way out here. Your air conditioner, condensing, evaporator unit should be operating in here, so you're taking into account the latent heat of vaporization. So when you go through a phase change, you require thermal energy, so you suck out heat. So you cool something, you cool your house. If you're operating out here, you're not using it. Okay, so liquid vapor mixture, we can define the average internal energy within my control volume, average entropy of a mixture, average enthalpy of the mixture, and we can write this in terms of these values. So now I'll go to the appendix in the back of the book. So table A4, and I went a little too low, so I'm gonna just get rid of the A4 up top, and I'm gonna underline $100. So temperature of 100 degrees. There is a corresponding saturation pressure. So 1 atmosphere equals what? Okay, so you're doing it in those units. Let's think in kilopascal. 1 atmosphere, we're at sea level, so we're pretty much at 1 atmosphere, right, in Florida. 101.3 something something, right, kilopascals. Okay, so we're close, right? But this isn't, so we're close, right? But anyways, this is basically 1 atmosphere for all argument's sakes. 100 degrees C, at 1 atmosphere, water boils. Come all the way across. I look at HFG, so I'll just put a line on there. And then HFG, I circle that. It has units, right? Kilojoules per kilogram. That's the latent heat of fuel. Okay. Now, I can go all the way up to a temperature of 25 degrees C. In order for liquid water to boil at 25 degrees C, right, I have to depressurize it. So water boils at 25 degrees C at 3.2 kilopascals. Who here has heard of a pressure cooker? Quite a few people. So if you want to cook food and you want to avoid boiling, or you want to accelerate the cooking, or in some ways when you pressure cook, you force a lot of the spices into the food too. But a pressure cooker, you put the lid on it, you seal it, and it develops pressure inside. So you're at a higher pressure. So you end up over here. So the water, if it was at 100 degrees C, you actually are not boiling within your pressure cooker at a higher temperature. You're not boiling the water because you're at some higher pressure. But yeah, anyways, nevertheless, 100 degrees C, water boils at 1 atmosphere. If I increase the pressure, right, then water boils at 120. If I decrease the pressure, I go to the top of Mount Everest, right? Water evaporates really quick, and that's why a lot of people, these climbers, die, because they open their body, you get water sucked right out of you because you're at low pressure, so all the liquid in your body wants to leave. So water, boiling is one thing, but it's the same thing as evaporation. Boiling is just a bubble, a nucleation bubble that forms, but really it's the phase change process, which is shown by these bell curves. And here's just a table that illustrates all the properties of water as a function of temperature and pressure. So internal energy is a state, right? It's related to equation of state. Entropy is related to equation of state. Enthalpy is related to equation of state. Equations of state are dictated by intensive, right? Two independent intensive properties. So here I'm talking about the properties of water in regards to thermodynamics. I'm listing them in terms of a temperature and pressure, so I can get the internal energy of of water, right, in the fluid state, in the gas state, or the fluid state in terms of a phase change in the gaseous state. I can do that same thing with enthalpy, right? At a given temperature pressure, I have the enthalpy I change the temperature and pressure, I change that. Latent heat diffusion, same with entropy. I define the temperature and pressure of my fluid in a control volume, and I have its entropy per unit mass. Now all this, we could make big S's and big U's and all this other stuff, but it's more convenient. You define a control volume, you define, have a density, so you know how much mass you have. You can convert from control volume to control mass, back and forth. You just need to know the density. Now, of course, the density is also a function of temperature and pressure. So, room temperature, if I look, so this is 1 over density, so a really small number is really big, right? So as I increase the pressure, well, it doesn't quite work that as nice as I'd like, but because I'm doing it as a function of temperature too. So so let's just say, yeah. I'm trying to illustrate that as I increase the pressure, the density goes up. But anyways, it doesn't quite work that way. But anyways, I have the specific volume or inverse density as a function of temperature pressure. So it also lists that. The gases phase, so really big number, really small density. Gases have small density, right? Really small number, high density for specific volume. So these tables you'll end up using if you do anything related to thermodynamics, heat exchangers, chemical reactions, whatever it might be. As an engineer later on, you're going to want to look up tables like this to get the properties of the materials. So somebody went through a lot of work to generate this table for you of water. They put in a lot of work to do this for various gases. There's a table like this for air, not quite for air, but I mean for refrigerants that are used. Like in your refrigerator, there's a fluid that is used in your refrigerator to cool your refrigerator. They don't use water, they use a refrigerant. There's a table for that. So here's the pressure one. So I can go to 101.3 kilopascals. Water boils at 99.97 degrees C. Go to the top of Mount Everest. The pressure is probably on the order of 20 kilopascals. Water boils at 60 degrees C, right? It's pretty much our body temperature. It's getting close to it. So you can see that the water really wants to leave because we have the water really close to the saturation. And then we have all these values for specific volume, internal energy per unit mass, enthalpy per unit mass,